Shall I? Yeah, okay. Ah, yeah. All right, good morning. Morning, yes. So yesterday we had this kind of qualitative or phenomenological discussion of many-body quantum systems, chaotic quantum systems, as opposed to single-body. We discussed various aspects. In the second half of the lecture, we were zooming in on the structure of spectra. And what I would like to do now is I want to recap where we were, more or less. I mean, wrap this all up. Then we will kind of focus this discussion and formulate relatively precise expectations as we what will we see if we compute, say, by means of correlation functions, properties of spectra of many-body systems. I mean, we will define some anticipations. And this will be the pre-stage to making all this concrete. I will then introduce the SYK model after all, and we will do some computations for the SYK. And I want to show you some also some numerical results which then confirm these kind of computations. This will eat up much of the time for today, and I will then reach a stage where you have to make your choice. I mean, you remember we had this, I defined these two options where we can go. I still haven't made up my mind, so I leave it to you. And I ask you, and depending on the outcome, we will then go a little bit into either of one of these directions. That's the plan. Okay, so let me, chalk. Yeah. Oh, yeah. So where were we? I mean, the situation was, if you take either a single particle quantum system or a many-body quantum system, put it on your computer and look at what you get for a given realization, you will see a spectrum that looks schematically like this, lots of levels. And we want to quantify the statistics of these guys and in particular distinguish between S and M. One thing I kind of argued yesterday was that what they have in common is there's almost regular spacing of levels on a micro level. And I also argued that this structure, or what's kind of underneath this structure, is at first sight, I mean, maybe somewhat unexpectedly, is a symmetry breaking principle. So we had this discussion, which was kind of not fully explicit, but I tried to motivate it. Let me just recap, I mean, or just formulate that this kind of micro statistics I mean, for me, it will be important to note down the following two facts. I claim that it can be analytically or precisely computed in terms of a kind of partition sum, which has a strong degree of analogy to that of a magnet. And the basic building block was micro statistics described by the following. I write down a single formula, and you will see in a second why I need this formula. So something like symbolically a partition sum, where we integrate over these Goldstone modes of our partition, of our symmetry breaking, which I noted yesterday. And then comes a very simple action in which we see two parameters. The first is the frequency spacing in which we want to probe in our correlation functions. Then we make it dimensionless by adding here the average density of states, which is depends on where in the spectrum we probe the system. So let me write this. And then came this somewhat funny expression, if you see it for the first time, I mean a trace of q times tau 3. I will not need this integral in full form. I mean, I will just say that it exists. And from it, you can compute correlation functions. And I want to mention three of them. And I'm sure you have seen them here. because they're so important. I mean, everybody uses them. And correlation functions. The first of these is the famous two-point correlation function, R2 of S. This symbol has appeared here, huh? R2 of S or R2? Okay, I write it down. So what does R2 of S do? It's a dimensionless object, so you take the average level spacing, delta, of epsilon, which is 1 over rho bar of epsilon. And then you ask, how are density of states correlated? At epsilon, say, plus omega over 2 rho of epsilon minus omega over 2. You take the cumulative average, minus the independently average density of states. And this is a function of a dimensionless parameter, S, which is pi omega times delta. So this is the correlation function which, well, I mean, I guess most of you have seen it. Let me just note down how it looks qualitatively. So this is more or less the structure which we get. And there are two important features, or three actually. It starts at -1, typically. This is level repulsion. You will never find two levels at the same point. Then you see this almost oscillatory structure which reflects an almost crystalline ordering of levels at unit level spacings, or this S parameter in dimensionless units. And here you have a power law decay. So that is what they all have in common. The second correlation function I want to mention is a form factor. I'm just introducing this because I will make later reference to them in concrete cases. So we tau, which is the Fourier transform of R2 of S, and the form factor typically has this structure. This is now actually the concrete form for the case of unitary symmetry, just Hermitian Hamiltonians, where you have here tau, which is Fourier conjugate to S. So it's in a way, it's not in a way, it's precisely time, a time-light variable measured in units of the Heisenberg time. And the Heisenberg time is 1 over delta. So this is what you find if you compute R2 of S, the Fourier transform in the unitary case. In the other symmetry classes, the structure here looks a little different, and also here, but this is again a detail for me. No? And the third one I would like to mention is the number variance, sigma 2 of E, which is just defined as the fluctuations of the number of levels in windows in the spectrum of width E. And the point we want to note down here is that due to this crystalline ordering, these fluctuations are very, very low. So if you take a window of width E, you almost always have the same number of levels in it up to logarithmic corrections. And this here scales typically as a logarithm of E over delta, and therefore looks schematically like this. Sigma 2. So these are the three correlation functions which we often use. Okay, so far? Good. So again, this kind of micro fluctuations, many-body systems and single-particle systems have in common. Now, where's the difference? The difference is, we discussed this yesterday, that the many-body spectrum, in a way, breathes from realization to realization this characteristic spacing changes. And now I want to draw your attention to one point, which is, one of those is perhaps not entirely obvious. You see that in all of these correlation functions, deltas features. And if you want to understand on an order 1 level, how will a many-body system differ from a single-body system, all you have to take into account that for the many-body system, this parameter, that parameter, and that one, they are statistically distributed. They fluctuate systematically. And once you understand that, you have more or less the structure of many-body spectra under control. We can ask ourselves, how will this manifest itself? I mean, now qualitatively. For example, here, this corner is situated at tau precisely 1. If you fix now your physical time, this is the actual variable, and take these fluctuations into account, you will notice that this one here, or you predict that this one will be rounded by many-body fluctuations. And the degree of this rounding has to do with the variance of the degree to which this here fluctuates, and it gives you a certain rounding window. Yes. If this here fluctuates systematically, you will realize that, these fluctuations can't be just logarithmic. So they must be actually, it's a very easy estimate to say that if you have a constant variance in the fluctuations of this guy, there will be a deviation here, and it increases quadratically. I mean, we can actually make, let me just show you, how such an estimate goes. You write down what is sigma 2 of epsilon. It's in fact integral dE prime. You count the number of levels, rho of E prime. This gives you the fluctuations in the number of levels. And if you now notice that this here breathes, then you will say there is, at large energies, you can estimate this here by some constant. This is this breathing mode on large scales, and you have 2 energy integrals here. So you realize that this will scale as E squared. For very short separations, this kind of crystallinity here dominates. So there will be a crossover from log to E squared in this correlation function. This is what we would expect. And less entropic, not chaotic. Oh, yeah, sure. But yeah, that's actually a super important and deep point, which I haven't touched so far. So all I'm saying is actually physics at scales. Okay, you can ask the question. I give you a many-body system. You can ask, when do you become ergodic? Exactly. So this, and there is a certain time scale associated to it, and this time scale we usually call the Thouless time. Now, this is the old school way of thinking about it. In many-body, in single-particle systems, there is a well-defined time scale, you can say. In many-body systems, this is a super complicated question because there isn't even a single well-defined. What the Thouless time is may change from observable to observables, and I have tried not to touch this aspect. This kind of simple phenomenology exists on top of that. Yeah, and now we can ask here. In this case, I would actually define the Thouless time as a time scale where these fluctuations take over. If we agree that the Thouless time is the time scale where you deviate from simple random matrix. Yeah, you can use this as a working definition. I'm not sure in this many-body context if we will ever have a... Yeah, of course, yeah, yes, yeah. Mm. Yes. Very good, yes. Precisely what you are alluding to is that the actual spectral form factor looks typically like this. Hmm? No, this here we have. Yes. And the connected part doesn't have like the initial decay because that is... let's not... Are you asking whether it starts from here or here? Yeah. No, all I want to say is that there is pre-random matrix type physics, which typically looks like this. So it's actually very good that you bring this up. I mean, you can say, this is my Thouless time. But then I will say these fluctuations we're discussing now influence the physics at timescales way beyond the Thouless time, namely at the Heisenberg time. And so it's all a bit intermingled, and I'm not sure, this is how life is. I mean, there is no simple one-does-it-all answer to these questions. Hmm? Yeah. Yes. Yeah. Yes, but what is undeniably true, and I will show you the numerics, that because the level spacing has these sample-to-sample fluctuations, you see a deviation up here. Hmm? And come again? No, that's actually very. This is a wonderful question. Look, this year is in a. Is due to is to fluctuation modes which make this beast here fluctuate. Now, I mean, first of all, I want to say that this time scale doesn't have to be the inverse of that time scale. That's where confusion number one starts. Yeah, and because there can be few long-lived modes, which, because the time form factor is exponentially sensitive to time scales, give you a relatively strong signal here way above the time scales which you would estimate from here. Yeah. And then in addition to all that, and I don't know how to conceptualize it, we have this signature here at very long time scales, which is almost trivial. Yeah? It has only to do with the fact that this scale here fluctuates. And yeah. I think, I mean, yeah. Huh? Yeah. Yeah, this is a central limit thing, which I tried to tell you yesterday. That the spectrum is just softer. It's Gaussian, not semicircular. But the best answer I can give. Yeah. So, right, I mean, my own way of thinking, pragmatic way of thinking, if one takes the fluctuations of this beast into account, one already gets, I mean, one can understand this here and that. This stuff is living yet on top of all that, and this is essentially non-random matrix physics, which these can be nonargotic modes, and I haven't actually touched them. And I mean, sorry to say, it sounds maybe sound a bit confusing. So we have different channels out of which these phenomena originate. Hmm? Yeah, I would say yes. Actually, I can connect to the previous talk. We have many observables which say related to some decay phenomena in many body systems. which at short times show Fermi-liquid type behavior, are at long times described by the spectral form factor. And I mean, in a way, this has also to do with Poincaré recurrence. I mean, this here is a single level is here probed, and I mean, at very long times. And this rounding is then seen in these observables. Yeah. Yeah. So these are our expectations. Let me say just a few more words on the manifestations of these. We already had this yesterday in a way on the manifestations of these collective fluctuations at the spectral edge, because I also would like to show you some data later on. So collective, I just draw some pictures here. At the edge, spectral edge, yeah. So in the single particle case, the situation is relatively clear. We have a crystal, I mean, a super hard Wigner semicircle sitting there, or a band edge of a many-body spectrum. Somewhere it ends. The level spacing actually gets a little larger here towards the end. I mean, the better way of drawing it would be like this. But then there is an ultimate last level. And if you now average, so you obtain the following density of states. Well, it's maybe like this here. So this is the edge of a semicircle. This is typically, not typically, it's generically, is square root behavior. So if you have here some epsilon naught, this here is epsilon minus epsilon naught to the power 1/2. And then the spectrum is so incredibly hard that it knows about this crystalline spacing here. So if you look closely, you find there's a tiny tail, and then you see here some oscillations which reflect this kind of crystalline structure, and it's quantitatively described by some Iry function. But so this is typically how these spectra look. In the many-body case, we have the following situation. We again have our, for a given realization, it looks like this, like here. But then for the next realization, the level spacing will be a little different. So I don't know how to draw this. I mean, the level spacing is now shorter. I'm exaggerating here, yeah? Like such. So what does it mean if you do the averaging? It means that you, in a sense, average over lots of these curves, which all individually looks the same, but the height of these guys differs. But since you have a conservation of the total number of levels, the extension here must also differ. So it's, one curve could look like this, the other one more like this, and then there's one in between. So you average effectively from realization to realization over many of these curves. And what you expect is that, first of all, these nice oscillations get killed. They get washed out in the process. And on average, you have something like something which looks more like this. Yeah. And now you say, oh, who cares about the fine structure of the spectrum at the edge? The answer is, well, it depends on the field. In many-body physics, we are sometimes interested in ground state properties, so we want to know. The main difference for looking very closely, or motivation for me, is the gravity application. In gravity, everything is about the edge, so you really, really, really want to know how the spectrum looks here. Yeah, sure.
You're thinking in this order system in some kind of ensemble average in the many-body case, because you can have also that Gaussian tails for only one single realization without any disorder in a large n limit.
Which system?
For example,
Bose-Hubbard, yeah, but what I have in mind here is something like this SYK, which is chaotic all the way, hard quantum chaotic all the way down to the bottom. For Bose-Hubbard, I would argue that if you go close to the ground state.
I'm sure that the argument works if you are like different realizations of the, you are like have a Hamiltonian ensemble to average.
Yeah, but the question is, do you, in your Bose-Hubbard realization, do you have spectral rigidity all the way down?
Yeah, you have actually the there are very strong fluctuations, not around the ramp, but rather in the plateau structure.
The plateau structure.
In the plateau.
Yeah.
Because, well, when you make the sample average, what do you kill with the sample is the fluctuations around the plateau.
Yeah, but
And the rapid, the specular rigidity,
yeah.
always like it seems.
Mm-hmm.
Yeah, I was wondering if that.
No, but what are you? What are you saying now? I mean, you say you have a Gaussian all the way down to the bottom of the.
Yeah, it's not necessarily they need an ensemble to get the Gaussian in.
No. I mean, for the SYK, you have also a Gaussian in the. A single realization. Yes. Yeah. It's a Gaussian in the center of the band, but then. Actually, now I want. I give you the formula later, and we will discuss. And then we can pick this up again. But yes, spectrum is Gaussian in the center of the band. Good. So this is more or less. I mean, all a bit of qualitative anticipations. Yeah. Yes.
Remember, when people in gravity they are excited about SYK exactly because it's much less Gaussian than the other models, right?
SYK will always be Gaussian, no matter what the gravity people say. I mean, I think they agree. In the center of the band, at the edge of the spectrum, it becomes a sinh function, a sinh of square root of energy. Yes. And I'm not aware of a single simple argument that, but I will discuss the origin of this. Good. So I may have stretched your patience somewhat with all these qualitative or schematic discussions. I will now really introduce the SYK, and then we can be a little more concrete. There won't be any hard calculations we are doing, but I want to be a little bit more explicit than before now. So you can, let's just, start completely afresh, and you can erase everything we had so far from your head for the time being. And I introduce now the SYK model. Who has seen the SYK model here? Oh, hands up. What? Who has not seen the SYK model? Never, ever. Okay, quite a few people. Very good. So what is the SYK model? Like I said, think of it as a many-body quantum chaos harmonic oscillator. The SYK model is called SYK model for Zashdev, Ye, and Kitaev, but it wasn't introduced by Zashdev, Ye, or Kitaev, but actually 20 years earlier, before Zashdev enters the stage. And it has its origin in nuclear physics. So we are going to 1970 now, about 1970. History. 1970. There were attempts in nuclear physics to refine random matrix theory. And I'm not good with this history, but I think the mindset then was the following. We had heavy nuclei. Heavy nuclei had this micro-scale spectral fluctuations, which we discussed. I mean, they were seen in resonances. But then it was also clear that the nuclear spectral density was nowhere near a semicircle. So it was, nucleus, the micro-scale spacing fluctuations were very well described by random matrix theory, but the collective spectral structure not. And people tried to come up with models which describe a nucleus somewhat more microscopically than RMT. And the proposal was, and these proposals go back to, key names here are French, the young Bohigas, later my PhD advisor, Weidenmüller, and a whole lot of other people too in this field. So they wrote down an effective Hamiltonian for a nucleus, and they argued that and the nucleus has strong nuclear interactions, so there are CK, CL. We can consider, hadronic fluctuations, creation and annihilation operators. And otherwise, we have very little knowledge, so we write here statically randomly fluctuating constants, which describes these matrix elements between these guys, and sum, and assume a Gaussian statistic for these. So these were the models which were proposed then. And the name came, since you in this way, you have an exponentially high dimensional Hilbert space, it's d-dimensional, and you embed few random interactions in it, they were called embedded ensembles. I think this is the origin of this term. And depending on the nature of these, whether these are real or complex or have some spin structure, there was an embedded GUE, embedded GOE, and embedded GSE. So this was the embedded ensembles. Now, what was understood about these models? Not so much, actually. It was relatively easy, even by 1970s computers, to find out that the density of states is Gaussian. So this was good. Gaussian density of states, as opposed to semicircular. Otherwise, I would say not so much progress has been made with these. So the computers were not strong enough to get more information out of this relatively complicated model. And analytical progress was considered to be not possible. That was a mistake. The analytical progress is possible. People just didn't figure out how in the early days. Yeah. So that's 1970. So 1990 comes Zastev and thinks about random magnets, condensed matter, totally different, not knowing this. And he introduces the Zastev rediscovery. And he also has, this is his contribution to this field, he does two things. He introduces a very nice path integral formulation of the averaged Hamiltonian of this, which we may discuss depending on your decision later. And he realizes, but only, not really clearly, I think, that there is an enormous symmetry, hidden symmetry here in these models. So with Zastev and actually Ye, they do this together. And then much later, 2015, comes Kitaev. And Kitaev is motivated actually by holography. So his thinking is the following. At that time, mid-90s, people had understood holographic principles relating black hole physics in d dimensions to quantum physics in 1 dimension lower. And there is one nice work example by Maldacena, which is super Young-Mills in n equals 4. So a complicated model. And Zastev, his way, I think the way Kitaev thinks, let's think of a simplest possible realization of a holographic correspondence, namely that between a 2-dimensional black hole, fictitious 2-dimensional, and a 1-dimensional boundary, so quantum mechanics. And this 1-dimensional model, quantum mechanics should have just time. Time is one coordinate, and it should be chaotic, as chaotic as it comes. So he proposes a model system which is chaotic and 1-dimensional, and that is very closely allied to this here. What he does is the following. He writes down a Hamiltonian sum over I, j, k, l equals 1 to n, j, I, j, k, l. So everything identical to these. The one difference is that he replaces these complex fermion operators here by Majorana operators. So let me write them down, and then chi I, j, I, l. So if you are not familiar with Majoranas, this is absolutely, yeah? Huh? Chaos, because we all believe that black holes swallow all information, make it totally entropic and maximally entropic, as like a random matrix, and then spit it out again. Yes. Yeah, exactly. So the chaos of black holes, yeah. So what are these chi's? They are operators. I motivate in a second why these chi's. Let me first tell you what they are. So they are operators, like fermion operators, but they have a commutation relations, anti-commutation relations, which are a little different from fermions. They have ij, like this. And if you are not familiar with Majoranas, I mean, it's no big deal. You can think of these. I mean, suppose you have a fermion, yeah? So you have a fermion Ci, and you take its, in quotes, its real part. You consider this operator. This is now a Hermitian operator, and I give it a name. I call this here chi, and give it an even index. And similarly, I can define the imaginary part. It's another Hermitian operator, and I give this here the name chi 2I plus 1. So in this way, we demystify these Majoranas. Starting from fermions, they are defined in this way. You can equivalently, you can define Ci as essentially this plus I times this, and in this way arrive at this model. Now you might ask, why the heck, why do we make our life complicated and work with these crazy Majoranas instead of fermions? The answer is, and that's an important one, this model here is much simpler than that. And why is it simpler? Because here, if you ask yourself, what are conservation numbers of this model? I mean, what does it have? So question to you, what is conserved here? Do you have any quantum numbers that are conserved? Particle number, right? Particle number, now you must say, oh, that's great, particle number is conserved. But in fact, it sucks. Your Hilbert space decomposes into blocks of conserved particle number, and then you always have to make sure that you work in the correct block, and you have to work with this Hamiltonian. Say, I want to work in the sector with 28 particles. It just makes life actually complicated. Here, we have broken particle number conservation. Well, you can see this intuitively. If you plug in this here, you get all kinds of combinations, C dagger, C dagger, C dagger. And so the particle number is not conserved anymore. Only the parity of the number, whether it's even or odd, is conserved, but not the total number. And this breaking of the symmetry makes this here a more random, and random means always simpler model. Another way to think about it is if you plug it in, here, this definition here, you get everything, yeah? You get C dagger, CC. In particular, you get terms which are characteristic for a superconductor. So you can think of this here as, if you want, the maximally random superconductor. So, interacting. So this is simpler than that. These guys here, I mentioned, they are random, and so they have a variance. And let me fix this. JKL. Everybody normalizes them in the same way. We normalize by 1 over n cubed. Then we have an energy scale which we call J squared. This is the high energy scale in the model. It sets, determines the bandwidth. And we always put here a factor 6. Why 6 here? Because then we spare ourselves 6s appearing later in calculations. Okay, so this is the SYK model. Any questions? No? Good. Now we want to understand. No? Yes. Yeah, right. If you plug them in, you get them in all possible combinations. And it's the simplest pair interacting model which allows for these particle number violations in a superconductor. Yeah. Yeah. What again? Yeah, I hope I understood you. Some kind of what? I think I'm maybe I'm misunderstanding you, but I'm saying something very simple. If you start here, say, if you let this Hamiltonian act on a state of a definite occupation number, it will change it. That's all I'm saying. Hmm? Yeah, but I mean, the actual statement I'm making is even has nothing to do with spaces. It's much simpler in a way. Say if you take this Hamiltonian, you let it act on a 5-nucleon state, it will always stay 5 nucleons. You get superpositions of different single particle states, but always total number is always 5. And this one here will change it. But yeah, that's all. Good. Okay. Now, one point which is important at this point stage here, we want to understand the physics of this, and so we want to pass at a very early stage from the second quantized formulation to a matrix representation, yeah? And then compare to random matrices. So we go from H, which is second quantized, we pass to H first quantized. And the question is, then we get a matrix. And this Hamiltonian, and actually, I could have the J's, we can take real. So we can choose them as real numbers because we are working here with this real and imaginary part, so that's fine. Question is, what symmetry class is this Hamiltonian in? Is this just Hermitian, or maybe it's a real symmetric Hamiltonian, or maybe even the symplectic Hamiltonian? And this question actually turns out to be quite tricky. I mean, this is, so let me first give you the answer to this question. This here belongs to, let me use this abbreviation, unitary, orthogonal, or symplectic class, depending on what? We assume this here to be even for simplicity. It's not natural to work with odd numbers of Majorana, so let's assume this here to be even. In this case, n over 2 is an integer. And what matters is the value of n over 2 modulo 4. So if you go on a computer and ask yourself, what is my n over 2 modulo 4, you have 2 options, 0, 1, 2, 3. And depending on that, you are in the orthogonal class, unitary class, symplectic class, or unitary class. So if you, and this is super important if you do numerical analysis, yeah? You would like to do some scaling, say, go from n, I mean, it's getting exponentially harder, from n equals 15, 16, 17, but in each step you change, unfortunately, the symmetry class. So you can always jump. Say, if you want to be orthogonal, you can jump in steps of 4, which is extreme, real pain in the ass, because going from, say, 30 to 34 is impossible. How do you find this out? It's a super nice, I mean, game in playing with symmetries, if you are inclined to do that. I have, if you are interested, I have tagged some questions with hints. So I can make this to you accessible, depending on your motivation. So I gave you a kind of a cookbook, how to find this answer. And without stating, I mean, broken down to lots of little nice steps. I mean, if you're full of energy, I guess after this day you will not be. Yeah. So do we have a web platform or what, where we can upload something here? Okay, good. Yeah. So I can. Mm-hmm. Yeah. Of course. Yeah. Yeah, you can break it by hand, yeah. Yes, no, absolutely, totally. Okay, so this is SYK and its definition. So now, yeah. Yeah, I mean, you can introduce some additional structure, or you can introduce here some additional operator. No, with that not. As long as if it's real, no. Yeah. No. Yeah. Yes.
I have to like stay with the representation of the Majorana fermions, right? So one of will be this one.
This one here?
Yeah, one possible representation would be
Yes.
to use fermionic operators.
Yeah, that's a very natural one. You go to an occupation number.
But then you will have that you don't have particle conservation.
No, you have not.
So
Why do you say you have particle number conservation?
no, I will not have.
You don't. Yes.
So how, if I want to make some dynamics, that will mean that at the end, I will like, during time evolution, like change from the symmetry class of my problem.
Careful. Maybe this n is not the number of particles in your Fox. Okay. This is the number of, you choose simply 28 Majoranas. You give them colors, yeah? Red, green, and so on. So this is this n. But this is totally different from the occupation number in the function. Yeah, totally different. Right. So let's now do our first exercise here with this guy and try to understand why the many-body density of states is Gaussian. And remember, yesterday I argued in hand-waving wave with the central limit argument, lots of independent operators, most operators commute. And I will now use these kind of arguments, but make them quantitative, and then we will see how the density of states comes out as Gaussian for this model. And this goes under, it's now about the collective fluctuations, spectral fluctuations of SYK. Fluctuations of SYK. And we do it like this. We are now really interested in the density of states. Many-body density of states, but in this language. Interested in density of states. So what we compute is rho of epsilon, density of states at epsilon. In the usual way, it's -1 over pi imaginary part trace over Fock space of G plus of epsilon, and G plus of epsilon is simply 1 over epsilon plus -h, our SYK Hamiltonian. So this looks like a like it really sucks. I mean, because it's a complicated beast. But we can actually compute this relatively easily. And the way to do this is first to introduce some economic notation. So I introduce a shorthand notation. I call this sum here over ijkl. I abbreviate it as a sum over a index sigma. And sigma is simply ijkl, right? And I then abbreviate this guy here as this, and then I have x sigma, and x sigma is simply this beast. Now, there is a mental note to be made. Note, I'll write this down here. This is a very friendly operator. And why is it so friendly? Because a consequence of this here is that chi squared equals 1. So a single Majorana squares to 1. And if you have this and write down what is this beast squared, you have since they all appear twice, you will find that x sigma squared is also 1. So these operators square to 1, so it makes them very, very friendly. Another nice thing is for n to infinity, if you ask what is the commutator between typical X sigmas and typical X sigma prime. I mean, you choose some of them on your computer, yeah? And most of them will have no Majorana in common. If n is very large, you take 4, another set of 4, most of them will be different. And these operators commute in general. There's very few exceptions of operators which do not commute, but these exceptions scale as 1 over n powers. Yeah? Then, how many sigmas do we have? It's also another thing. Sum over sigma 1. We have these here, but since we choose them to be all different because Majoranas of the same label square to 1, so you have, give or take, n to the 4. Yeah? N to the 4 divided by 4 factorial, so, but of order n to the 4. And I call this number, I call it k. So this is what we need to know in order to compute now this beast, approximately. And what we do is we do a brute force Taylor expansion here in H. Yeah? So we write this as this G. We write this in the following way. I'm using now a diagrammatic code where to zeroth order we have just 1 over epsilon. Then to next order we have this beast. There's a single of these operators sitting here. I label this by sigma, and this is J sigma X sigma sitting here. Yeah, it's just a graphical representation. And then it goes on. 1 sigma prime plus of the order of. Understood? This is just a formal representation of this Taylor series. Nothing happens here. I'm just using these dashed lines for the Hamiltonian. Everybody here? Yeah? Now, what we are actually interested in is the density of states averaged over realizations. So we write on this. And average this beast. Yeah? So what can we say? This guy doesn't care about averaging. This one gets killed because the J's are Gaussian distributed. There is a single one. The first interesting one is here. And here we get nothing unless sigma equals sigma prime. If sigma is sigma prime, then we have 2 X sigmas here, one from here and one here, and they square to 1. So what we get is this one plus this here. I'm writing here a single line now for this averaging. And what we'll have here is this variance, here, this one, times k, because we're summing over sigma. And I introduce a number for that. We have 6j squared over n cubed times k. I call this gamma. This is one of the most important parameters in this game here. So here we get an assignment of gamma, and we can write down the analytical expressions down here. Here we have 1 over epsilon plus, and here we have 3 epsilons. 1 over epsilon cubed. So we are almost there. We continue now this game, yeah? And at cubic order, there's nothing. At quartic order, we get a few contributions. We get this here, excuse me, this here, where they, overlap, and also this here. They only differ in the ordering in which of these J's we average. Yeah? Now here, for example, we have here x sigma, x sigma, x sigma prime, x sigma prime. Here with x sigma prime, x sigma prime, and similarly here. Yeah? And then it goes on, and this is a typical structure of such a series, of these diagrammatic series in many-body perturbation theory. So it looks like totally generic here, But now I'm claiming there's a massive simplification we can make. So any ideas of what could simplify, or what instance simplifies our life here and effectively allows us to sum this series? Come again? A little louder. I still didn't understand. Yeah, right. My hearing, it's
you have to realize why, to which order does each diagram contribute?
yeah, that's stating why it's so complicated, but now I'm saying it's, in fact, we don't have a complication, it's all very simple. Due to a reason which I mentioned. Yeah. I mean, for any kind of impurity perturbation model, you would get this mess here, yeah? Oh, yeah, sure. Yes, yeah, exactly, yes. Yes, absolutely. Yeah, right. This is what we usually have in solid state physics, and what I'm saying here it's the radical opposite. Because of this. You know, normally in solid state, as you say, you would say, I mean, we have a tendency to say, oh, such a Gaussian graph is suppressed. And it happens in randomatic theory, as I will show in a minute. But in the SYK model, they only differ by the ordering of axes here, yeah? And since, but here, for example, you have x sigma, you have x sigma prime. But with a very high probability, they commute up to 1 over n corrections. So up to 1 over n corrections, which don't interest me for the time being, they're all the same. That's what makes it so simple. So what we get is here gamma squared epsilon to the power 5 times 3 for all of them. And now we can simply guess, or not guess, I mean, we can say how this series continues. What we have is, oh, now I have to sacrifice, yeah, here. So, the series goes like this. G of epsilon averaged is approximately up to order 1 over n. Sum over L equals 1 to infinity, or 0 to infinity. 1 over epsilon, gamma squared over epsilon squared. Oh no, gamma over epsilon squared to the power L. This is just counting. And what comes here? What should I write here? Which coefficient? Just how many contractions do we have in each order? Yeah, something. I mean, yeah, it's 2L minus 1 double factorial. This simply, I mean, what to begin with, I mean, this is, I mean, just to make it concrete, if we have all these different guys, 2L of them. So this one has to be paired with anyone. Yeah, it's the number of Wick pairings. Yeah. So good. So this is our series for the density of states. Yep. Now you would argue that this looks bad because there is this 2L minus 1 here, double factorial, which it's an asymptotic series the way it stands. I mean, for large L, this here will explode no matter how small this is. But then we did something which was slightly forbidden to begin with. We did a unjustified Taylor expansion. I mean, well, we did a formal expansion. And the way to wriggle one's way out of that is to apply Borel summation to this series. If you don't know what Borel summation is, I have another exercise where this is explained. So the trick here is, the trick to sum this series is to do the following. You write this here, 2L minus 1 double factorial, you write it as a normalized integral dt e to the minus t squared over 2 times t to the 2l. Yeah, you smuggle this guy in, and then all of a sudden the series looks nice, because now you have only this factor t to some, that is a geometric series, and then you do the t integral, which you can also do. And what you find is a Gaussian. This is a Gaussian, so this gives here, let me write down this Gaussian in correct form, 1 over gamma square root of 2 pi e to the minus epsilon squared over gamma squared. Actually, this was wrong here. Gamma squared times 2. So this is the Gaussian density of states. And the way to rationalize it, I mean, where does it come from? Is because we were adding here lots of essentially independent self-energy contributions, which are not strongly correlated. And that's the many-body aspect here. Yeah? What we also see is that the bandwidth is set by gamma. So, Oh, yeah, right. No, I want to call this here gamma squared, I think. Yes, sorry. Yes, and here it's gamma to the 4. Yeah, thank you. So it's Gaussian. We see that gamma sets the bandwidth here in this model, which is also quite natural. If you look at it, if you ask yourself, I'm a single Majorana, yeah. So if you are a Majorana, then you pick up a self-energy due to this here. You talk to lots of other Majoranas. The variance of this here is j squared. But then you also have to count how many friends you have to which you talk to. This gives you the factor k. And this then explains here this nature, this being effective bandwidth. Another way to think about it is to say, if we think here about this h, what we are doing here, we are adding n random coefficients. Essentially, all contribute to the energy. Each one has an RMS, which is given by this value. And then you add a square root of n central limit and arrive again at this gamma scale. So this is very natural to have this as a bandwidth. Yes. At the tail, this breaks down. This.
Is there a way to understand why one over n corrections are relevant there?
I'm sure there is. I don't know it out of my head. Yeah. But it's a very good point. I mean, would have been the next remark. I mean, this kind of has its limit. When the density of states itself becomes small, we must be careful with these arguments. So but you can, clever people, I should have told you, these diagrams in SYK jargon are called chord diagrams, like chords. And there is virtuosos out there who know how to play with chord diagrams. I mean, it's an art form, yeah? So people do this for a career, and they know how to go beyond this approximation. And what we find is that the actual density of states, so rho of epsilon, to a much better approximation, is up to a normalization factor, is the following. It's exponential of 2 arc sine squared of epsilon over 2 gamma. And if epsilon over gamma is a small number, this becomes a Gaussian again. So this is this Gaussian, approximately, in the center of the band. And it becomes a sinh of 2 pi epsilon minus 2 gamma over gamma to the power 1/2, close to the edge. And if this here becomes very small, you can forget about the sinh. So then it's a square root. This is the square root edge, yeah. So it's a funny density of states. It looks Gaussian. If you plot it, it looks Gaussian, and then it doesn't continue as Gaussian. It has here square root density of states edge. Huh? Large n, yeah. Large n, yeah. Large n, you need, without large n, you are screwed. Yeah. Good. Then, final remark here is, this is the average density of states. Now, I mentioned the density of states fluctuate from realization to realization. This we can easily compute by the very same, by these chord diagrams. It's a very simple calculation, actually. So what is the variance of the density of states? Suppose we want to know rho squared average at a given density of states. So what do we have to do? We have to compute the trace of two Green functions. One for one row, the other one for the other. So since it's the trace of the Green function, I draw a closed line beginning and ending somewhere in Fock space. And here I should introduce now all my chord diagrams. So all of them, yeah? And let me express the summation of all of these by yellow guy. So yellow is the sum over all chord diagrams and hence the average density of states. But now we have another density of states. Well, it's another yellow line. And like here, so this looks familiar from spectral statistics. Now, in order to make them talk, to make them connected, I need to draw some chords here in between. Huh? So remember, this is a trace here. So let's do something like this. Question: can this survive this diagram? Is it finite? I mean, it's good, right? It correlates the density of states. No, I'm making it, it's an ensemble average. Now, yeah, but everybody is happy here. The J's are all, I'm only averaging J squared, so the J's are perfectly fine. They're happy, yeah? But somebody else is not happy. Yes. So this here, this guy, is, by definition, is a trace of a single Green function averaged. And it is this here plus this here plus this here, and all these chords, yeah? And if we just saw, if we sum over them, we get our Gaussian density of states. But this is just, I mean, now I have two Green functions under the average. And there will also be contributions where I expand here in an isolated X sigma. So here we have an X sigma sitting. And here we have the same X sigma down here. And now I'm claiming this diagram is 0. And why is that? The reason is that here we have a trace over an uncompensated X sigma. So a trace over Fock space, over one of these Majorana guys. And yeah, these traces vanish. In order to make it non-vanishing, I need to bring another, this guy is lonely. It wants to have a friend down here. The same X sigma, yeah? So I need another one where I have, and now they are no longer lonely. Here they square to 1, which is nice. This diagram is happy. Same upstairs, but the entire diagram is much smaller than the ones without these lines. And the reason is I have here 4 x's, but only one summation. One, yeah. So this is the reason why this here is proportional to the average density of states squared times one missing sigma summation. So this is 1 over k. This is the variance of the density of states, and this is what I mentioned yesterday. Many body spectrum, typically, the density of states fluctuates from realization to realization. These fluctuations are, of course, proportional to the density of states. they are small, but not that small. They're polynomially small in n. So what we can do now is, we have now all the information together to actually understand the spectrum, because, well, the SYK is quantum chaotic. It will have the microscale fluctuations. It also has these collective fluctuations. We have them under control. Now what we can do is we can go ahead and take our spectral correlation functions, as I mentioned in the beginning, and plug in this here for the variance of the density of states and see how we fare against numerics. Yeah. Yes. Yes.
If the connected part is literally equal to the disconnected part in the square. So what is the reason that I should expect that this thing has like more contribution to the connected term apart from this one?
But to leading order, it's this.
Okay.
For each additional one, you're right. Of course, I can add here more lines. But for each line, I will have to pay another factor 1 over k. So this is the leading one. Otherwise, you're totally right. Yeah. Good. So we have everything together now. Yeah, lots of bits and pieces. But the essential ones are this insight that this is a chaotic Hamiltonian and this formula here. And I want to show you now some numerics. Actually, I mean, it's just because I'm proud of it. One can take the SYK out of the box and derive all this Goldstone mode action plus this stuff here. And we've spent a long time on doing that. But the essential physics I just told you, yeah, this is what this construction is. And I would like to show you now some numerics, how it looks against simulations. Yes. Zoom? Yeah. And why can't I just? Huh?
You can share the screen.
And if but if I just want to show you some slides. Yeah. No. And they told me that all I would have to do. Yeah. Mm-hmm. Yeah. Here. Good. Yeah. So it's in a window. No, let me. Yeah. So these here are various early numerical simulations. By early, I mean 16, 17 around of SYK models. The number of Majoranas there is in the 30 region. Yeah. So the first plot is the nearest neighbor spacing distribution. You have seen this, right? Nearest, I mean, simply level repulsion. Yeah. And what I want to highlight here is that it's super perfectly RMT, perfect. But which symmetry class you're in depends on the value of n. So these are cases where you are unitary or symplectic. Symplectic has this quartic behavior here, depending on n, and this is nicely resolved in the numerics. So this checks. Microscale fluctuations are RMT-like. The same for the number variance. Here we have GUE, GSE, GOE. It's beautifully logarithmic, but look at this treacherous guy here. This deviation is not numerical deviation. It's not Thouless energy. This is unsystematic. I'll show this in a second. And then we have here the form factor. I don't know how it was normalized, but never mind that. But I want to draw your attention to the fact that it looks GU-ish here, but this is a little less cornery than we might wish for. Yeah? And what I'm showing you now is that there's systematics here. This is the number variance at larger scales. I mean larger, and you see here this runaway. So this is the energy squared. And I should say that these calculations here, together with these, they come out parameter-free brilliantly. I mean, in the percent region. So this is super high precision agreement between numerics and analytics. So this works really nice. This is another representation of various form factors in different symmetry classes. You see here these little cusps. They are indicative of GSE. Symplectic has a. Then you see some severely rounded, this is GOE, and some more cornery, GUE. And here you have pre-Thouless time junk sitting around. Yeah, we discussed that. And if you zoom in now, you notice that this rounding here is not numerical junk again, but it's systematic. So here, these are calculations of this nonlinear Sigma model with these fluctuations taken into account, and these are the roundings of the corner which we discussed before due to the density of states fluctuations, and they're getting most pronounced in the symplectic case. Here. Symplectic case, you really have this rounding, and one can, this is really high precision numerics of Jacques Weber shot, quite nice, 28, and the red curve would be the form factor in the symplectic ensemble, and this is numerics versus analytics with these finite n collective fluctuations taken into account. So it really checks. This is very nice. I want to show you one more plot. This is unpublished, very recent. This is the density of states at the edge. And up here you have random matrices, just as a benchmark, with 9 and 11. I mean, 2 to the 9 and 2 to the 11 dimensional random matrices. So semicircle, there is this square root behavior here, and now you see here this crystalline, these Irish type fluctuations of a random matrix. And this here is a little bigger random matrix and shows the same behavior. For the SYK, these fluctuations are absent, and we have a much softer tail. But now look at this curve. There's p equals 4, means that this is an SYK with 4 Majorana interaction. But what you can also do, this is called the so-called approach to the double-scaled SYK, yeah? Yeah, p is the number of Majoranas you consider here. This is 4 of them. But you can generalize your SYK to include 6 Majorana or even 8 Majorana interactions. So then you have here longer strings, and meaning you inject more randomness into your Hilbert space. And there is a statement that when p squared scales as n, you actually have so many matrix elements in your Hilbert space that the system becomes dense. I mean, becomes now strongly entropic. So you should observe that a crossover takes place from a many-body generic few-body, many-body spectrum to a more random matrix, and this is what we see here. So this is SYK, but now with a super hard edge due to large number of Majoranas in the interaction, and you have this many-body crystallization of the spectrum. So one can take this crossover, and this is very interesting for people in gravity, because in gravity, in the gravitational path integral, you really have these structures, but from a more down-to-earth, many-body perspective, I mean, a model which has such a large number of interactions is not very physical. So that's a bit of a sobering news in this holography business. Boundary models which have few-body interactions are not really very well, not nicely consistent with gravity models. And this is, the sucker, yeah, in this game. Yeah. And that's basically it. So this is what I wanted to show about SYK spectral statistics and its kind of understanding. And I think my time is up now, no? I totally lost track. No, then okay, I think it's a good point, time to break. I have one more seminar, yeah? And we can now, we can make a decision. I mean, what I could do is I could talk a little bit about this gravity stuff. I mean, a connection between gravity and many-body quantum chaos in SYK context. So the way to for you to conceptualize this. It's a nice sci-fi story. I mean, there is strings and gravity and Einstein and all that, but it's not very useful. I mean, unless you want to go into holographic quantum chaos. Well, so it's a nice fairy tale. The alternative would be to turn to short-time physics of the SYK, meaning scrambling in this language, and how to understand from the SYK Hamiltonian, which is, I mean, I mentioned before, this guy wants to help us. For short times, it helps us in a different way from what I outlined here. And there's diagram classes, and then we can talk about OTOC physics and conformal invariance and so on. This is useful. If you want to do many-body quantum chaos in a condensed matter, this is part of an education, but it's maybe a little drier, yeah? I mean, so it's just computing diagrams and discussing OTOC physics. Up to you. I don't care. I mean, for gravity, I have a talk, lots of colorful slides. The other stuff I would do here on the blackboard. We can also skip the third seminar. No, this is a quantum computing talk I want to show. This is a quantum computer talk I wanted to do. Yeah, IBM quantum. Yeah. So this afternoon, officially there's a tutorial, but what I want to do is I think I have a very nice story to tell about quantum chaos in IBM quantum computers. I believe they are not very stable. For the reasons we are discussing here, it's a goal. So this is, would be, I think, is a very nice and totally afternoon compatible. I mean, not intellectually not very challenging story. Yeah. Huh? Yeah, you can vote. I mean, who would? I mean, I'm not asking who is for quitting this. You can, but who would like to know about this gravity application? You're too shy, like this. Okay, a little bit less shy. Come on. I mean, I have to identify a majority. Okay, and short time physics. Yeah, look, it's again, you have to be more clear. I mean, who is for gravity? Come on. Right. So now I'm really counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and short time physics? 1, 2, 3, 4, 5, 6, 7, 8. It's a close draw. Yeah. Okay, let me tell this gravity stuff, and then yeah, it's yeah, yeah.
What happens if you change that boundary? Can you
This one?
make the SYK model irregular?
This one? No, no, because you have only one parameter in this. There's no parameter to compare with. What you can do is you can write down a two-body term here. And this is quite artificial, right? We start at fourth order, there is no two-body. Once you write a two-body term, everything changes. But, exactly. This would be p equals 2. And yeah, this would be, it's commonly called SYK 4 plus 2. When you have, if you have a two-body term, which is much more natural from the physics of this model is very different, but not with regard to what we discussed here, but rather with regard to the short-time physics. The SYK 4 plus 2 is a Fermi liquid. I mean, it's just fermions with interactions. This one here is a non-Fermi liquid. This is the main difference. No, the many-body diagram. You mean the contributes to the ramp? No, I don't know. I don't know of a good way of drawing this. I mean, it's. I can describe it in terms of one of these. We had it in terms of a kind of Lindblad type of equation, and then solve it in terms of a certain ansatz, which is maximally Fock space isotropic. So there is. It's. yeah, my answer is not clear, but there is no good way of drawing in Fock space a single diagram which gives you this. In this language, yeah, you have to do a basis change to a different operator hierarchy. It's getting quite abstract. We can discuss it in private. I mean, I can talk. No. Okay. I mean, you asked me. I give, everybody else can go. I answer this question in two minutes. Yeah. So the way how to do let's do Fock space diagrams. I mean, everybody else can go, but let's do Fock space diagrams for. Suppose we had never heard about this, and we would write down. Now we really try to write down the Berry diagonal approximation. So we write down this. So here we start in a Fock space state, N, and now we have lots of scatterings. Scatter, 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 everywhere scatter. Yeah? And we do the averaging. So once we do the averaging, we get a wild spaghetti of diagrams in principle. Okay, total mess. Now, do the following. Think of this as a quantum amplitude, and this here is a complex conjugate amplitude. Really quantum mechanics, yeah? This is retarded, this is advanced. And draw a cut here. So what you then, if you look at this, you have a propagator where you are locally here, you are in some state n, and here some state m. And here you have, it has a history of scattering. Very complicated. Now, you know for fundamental reasons that there must be one contribution. I mean, let's call this here some time-dependent propagator, pi n, which is labeled by these endpoints. There must be one contribution to this guy which is long-lived, which doesn't decay exponentially. This we need for unitarity, water identities, ergodicity, for all kinds. The question is, what is it? And the good way to think about it is to think about this as a bra-ket state, as a bra and ket. Think about this as a matrix in Fock space. This is what it is, yeah? Now, it turns out that you can, there is a basis in Fock space, a basis of Fock space matrices. I mean, there are d squared different matrix generators. You have d times d, so it's a d squared dimensional space of matrices. And we can, here's a good basis in which to draw it. You sum over all a, some coefficients. And these x's here are products of Majoranas. So x0 is just 1. Then there is x1 is chi. And so if you count the number of Majorana polynomials, monomials you can write down, it's precisely d squared. So they form it's like a Fourier transform. The diagrams you are after, the universal spectral statistics diagrams, are the ones where only x0 contributes, the unit operator here. Yeah? So if the contribution to this propagator, where this here is proportional to the unit matrix, it's one of these contributions. That is a long-lived contribution. And that gives you the universal random matrix diagrams. So you see now why I can't write down an explicit diagram for it. This is a zero-mode ergodic zero. It's natural, yeah. The unit matrix here is completely isotropic in Hilbert space. It's ergodic, and all others are decaying. This is on the idea, yeah, but it doesn't get any. Mm-hmm. Yeah. Oh. Hmm? Ah, this is no better. No, is it? Yeah. Ah, yeah.
Yeah, I was just wondering what's the dashed blue line there?
The difference between the dashed and the solid?
Sorry?
Ah, there is no dashed blue line. Yeah, I forgot. I don't know. I mean, the blue line, but the blue lines are right. I mean, the blue lines are what we get of our nonlinear SYK model with these fluctuations included.
Okay.
And we are struggling with a factor of 2. Could be something. I mean, some factor of 2 is not under control. Tobias did this. Yeah. I mean, and the red line is GSE, and the other one is SYK.
Sure.
Yeah.
But it's just a scaling then?
Maybe we have a bug in the calculation.
Okay.
I just don't remember at this point. I mean, this is a few years old.
That's okay. Just because it looks a little bit better, so it's just because it looks a little bit better.
Yeah, could
so
could also be that this is the best fit, and the blue is our analytics. So
is that a fit?
No. I mean, the blue is. I mean, the bad one is definitely parameter free.
Okay.
But maybe with a computational mistake.
Okay.
Yeah.
Okay. Thank you.
Yeah.
So no more questions? Okay, so thank you.
All right. Thanks.
So we meet at 2:30 for the next lecture.